I feel very confident I'll get the chemistry down right, but I may be a little more discombobulated than usual. So take a look at this reaction, T-butyl bromide, boiling water. What do we get out of that?
I mean, are you asking right now, or are you waiting for everyone?
Yeah, I'm gonna wait. I'm gonna give everybody. A few people wrote something down and looked up at me. A couple of people just looked at me. So I don't know if you already had the answer. A few people are still writing. I mean, it's not a quiz or anything, right? So it is the beginning of chapter 8. Okay. Anybody want to venture a guess?
I mean, I'm not sure about the name, but it's going to be an elimination.
It is an elimination reaction. So we only have one. There are 3 beta carbons, but they're all chemically identical, so they're all homotopic. We're going to get that. And this is an acid-base thing that's important to understand, right? So really the way this reaction looks is it would generate HBr. But HBr in water is always going to be H3O plus and bromide. And so really this reaction, if we forget about the solvent for a minute, right, the reaction is this T-butyl bromide undergoing an elimination to give an alkene and HBr. Right, again, you can go in here and you can add up the bond energies. You can discover that enthalpically, delta H would suggest this reaction would go to the left. Right? So if you just look at bond strength, carbon bromide sigma, carbon hydrogen sigma, hydrogen bromide sigma, carbon carbon pi. Right? So you're essentially, if you think about that, 2 sigmas on the left, a pi and a sigma on the right. Pi bonds are a lot weaker than sigma bonds, so bond strength would suggest the left is favored. And what typically drives this, if you do this reaction, is going to be the temperature. Right? So high temperature favors elimination. We've gone through this. The reason for this is entropic. Okay, so by entropy, we go from 1 molecule on the left to 2 molecules on the right. That increases disorder. The way chemists and physicists, for that matter, talk about disorder isn't like a cluttered room. It's all that we talk about it in terms of degrees of freedom. Like how many different ways can these things behave? Right? And if you think about this H and the Br, on the left, the H has to be close to the carbon because it's covalently bonded to this molecule. The bromide has to be close, right? The H and the Br can't go very far away from the carbons. On the right, the H and the Br have many more degrees of freedom, right? They can go anywhere they want, regardless of what this organic molecule does. So the more you can increase degrees of freedom, the more favorable entropy becomes. All right, so on the exam, if I had put this question on the exam, there probably was one pretty similar to it. You should have drawn the alkene, and I wouldn't have expected you to draw H3O plus and Br minus, but you could have.
Is that going to be something that becomes more important in this chapter, or not really?
It is exactly in this chapter. Okay, so basically, chapter 7, we show this reaction going to the right. In chapter 8, we're going to look at this reaction going to the left. All right, so this is the segue. All of chapter 8 isn't chapter 7 in reverse, but this reaction and the reaction of addition of water to alkenes is. All right, so if you know the E1 elimination reaction, you know this reaction. So let's look at how we might go backwards. We're going to go right to left here. All right. So in the eliminate, I tell you what, go ahead and draw a mechanism for the E1 elimination up here. There's one intermediate.
glare is just terrible.
Okay, so it's an E1 elimination. There's no strong base in this elimination. It's just water, so you got a weak base. So the first step in the above reaction is going to be the bromide leaving. Get rid of some of this stuff. Right, so the bromide leaves and you get a carbocation. So the bromide leaves, you get bromide ion, carbocation. And then to get to the alkene, bromide takes the H, the CH electrons make a pi bond. Right? Okay, so the reverse process has to go through exactly the same intermediates. And the reason for that is, if you think about an energy diagram, you know, you really want to think about an energy diagram, right? All right, so if this is our path to the right, if somehow we took a different path back to the left, and if we took a different path back to the left, these energies differ, and in effect, what you'd be doing is creating or destroying energy. Right? So remember your basic physics, you can't do that. So the pathway, the mechanism of the reverse mechanism has to mimic exactly the forward mechanism. Okay, so in this case, the way this mechanism is going to go right to left, the pi bond is going to attack the HBr. We'll go through here in a minute why that happens, because our intermediate has to be the same. It has to be a carbocation and a bromide ion. Right, so there's the same intermediate exactly. And now we need a carbon-bromide bond, so this bromide ion attacks the carbocation, and we get our Turk-Beetle bromide. This is called an addition reaction. It's specifically called an electrophilic addition reaction. So H and Br add to the alkene. I think seeing how this is called an addition reaction makes a lot of sense. It's called an electrophilic addition reaction because the HBr, right, it's receiving the electrons. So this is the acid, this is the base. That makes the acid is going to be the electrophile, and the base is the nucleophile. And specifically, the pi bond electrons are the nucleophile here. Nucleophile basic. So with HBr, this is simply a proton transfer. It's just a Bronsted acid-base reaction. It looks weird because the nucleophilic basic electrons are pi electrons, right? We like to think of pi electrons as being stable. And it is, more or less, right? This 2-propene here, if we put that in a bottle, it's a gas, so you have to put it in a pressurized cylinder. But if you do that, it will stay there for centuries, right? It's not going to react with itself. That pi bond is strong enough to hold the molecule together. Nothing's going to happen. But again, if you expose it to an acid or an electrophile, those electrons can then be basic and do a reaction. Okay. So your question, I don't know if you have questions. Any questions right now? I don't want to presume what your questions Okay, so you might wonder, how do we know which side, anytime I ever show a reaction, oh, this reaction can go to the right or it can go to the left, and how do you know which way it goes? And there's a couple of things. So the one you already know, you already have seen this. So higher temperature here is going to favor the right, the elimination. So you know this from chapter 7. Higher temperatures favor elimination. And that is mostly entropic. Okay, so at higher temperatures, entropy is more important. Fundamentally, that means at higher temperatures, the right side of this equation is more stable than the left. So what's the converse of that? If higher temperatures favor the right,
Colder temperatures favor.
yeah, so colder temperatures are going to favor the left. All right, and if you think about this, if you think about the equation, so the Gibbs free energy difference is actually dependent on temperature. So you can't just say, oh, that's stable, that's not stable. It actually, the free energy difference changes as the temperature changes. This winds up being a really critically important part of a lot of like industrially important chemistry. So you're probably all aware we get ammonia, right? There's 8 billion of us on the planet. We all like to eat, so we have to fertilize crops. You can't do that with 12th century technology, so we have to make fertilizer. Something like 1% to 2% of the electrical power that humans use a year goes to converting atmospheric nitrogen to ammonia. And that was discovered. It was really clever. It was a bunch of thermodynamicists who figured out how to do that, because the N2 plus H2 goes to ammonia equilibrium depends on temperature. You got to find exactly the right temperature where the reaction happens fast enough, but the ammonia is favored. Anyway, it's a fun story to read about. It's not going to be in this class. But as you lower the temperature, the importance of entropy diminishes. That means enthalpy is more important. And like I said, the stronger bonds are on the left. So if you ever look at a chemical reaction and you want to judge the effective temperature, the more disordered side will be favored at higher temperature. The stronger bonds are going to be favored at lower temperature. Good. All right, so that's our addition reaction. Let's think about, let's think about some of the implications of this reaction. This seems like this is not a big change, but go ahead and see if you can come up with a product of that reaction. Okay, so again, in chapter 7, that's going to be your kind of mechanistic paradigm. You're always going to be using the alkene pi electrons as a nucleophile. That's really the first half, not chapter 7, chapter 8, sorry. That's the kind of the first half of chapter 8. All the reactions in chapter 8 are additions to alkenes. So you're going to take your carbon-carbon double bond, and you're going to break the pi bond, you're going to add 2 different things to the pi bond. All right, so the general reaction will be something like this. That's our general addition reaction. And in all the cases, I'm going to ask you guys to know mechanisms. The pi electrons are going to go toward something, all right? The pi electrons in the alkene are going to be nucleophilic. But about, I don't know, I haven't added it up exactly, but about half the reactions in chapter 8, I'm not going to ask you to know the mechanism. I'll talk about the mechanism in class to try to explain why it happens, but I'm not going to ask you that mechanism on a test or a quiz or anything like that. But when we do, for the mechanisms you're going to see, it's always going to look like this. The arrows are going to start with the pi electrons, go to some reagent, and the reagent's going to have, a partial positive charge on the thing that gets attacked. So there's HX, there's water, there's X2. So there's a few of these we'll get through. So anyway. So here, the pi electrons are going to attack the H. Right, that seems clear enough. But now the issue is the H can only have one bond, right? Hopefully everybody's got that. Hydrogen can have one bond. We're using electrons that are currently shared between two atoms. So that H is going to bond to one of the two atoms. The other atom is going to be a positive charge. So here we have two options. Option 1, we put the H on the more substituted carbon and the positive charge on the less substituted carbon. Option 2, we put the H, in this case, we put the H on the less substituted carbon, we put the positive charge on the more substituted carbon. So which of those two cations do you think we get? Red or green?
Green.
Green. Why?
More stable.
Right. So this is the more stable carbocation. The book has a nice little picture of how this, the energy diagram for this, right? The transition state going to the intermediate is going to be closer in energy to the intermediate, so it looks more like the intermediate. So the transition state to get to the tertiary cations, lower in energy than the transition state to get to the secondary. That means you get to the tertiary cation faster. And then it's also more stable, so there's no reason to go away from it. Okay, so we are not going to see this. All of these electrophilic additions, right? The reactions where we take an alkene, we add an electrophile, we get a cation. All of those will always give the more stable cation. Right? Some of these reactions, like the one I put in the general addition, they're both secondary. Right? In this case, the cation here and the cation there are exactly the same molecule. But sometimes they're not. But if they're both secondary, you're going to get a mix. If they're both primary, you'll get a mix. If they're both tertiary, you'll get a mix. But you're always going to get, if there's a difference, you're always going to get the more stable cation. And then you're also, for either one of these, right, you're going to have not a bromide, sorry. You're going to end up with a chloride ion. That's going to be the nucleophile that comes in second. Okay, so what dictate the step that dictates where the chloride ends up is not the one that involves the chloride. Right? The step that dictates where the chloride ends up is the protonation. Right? If there's a positive charge there, we would end up with the chloride on the secondary carbon. If we get the tertiary carbon, it would be there. So chloride attacks there, and the product has the chloride on the more substituted carbon. Make sense? So almost always, for this whole thing, so in the addition of HX to an alkene, the H is going to go on the less substituted carbon, the X on the more substituted carbon. That is technically what's called Markovnikov's rule. I wish it was possible to talk more history of chemistry in this class. One, it's interesting, and two, what I would like to, this isn't easy to put on an Orgo 1 exam, right? Orgo 1, you're expected, my colleagues, when you go to Orgo 2, will expect you to know certain things. So to get through that, we got to go at a pretty good clip. But what I'd like to give you, if you're trying to process all this, technical detail, all this stuff gets hashed out in the lab. Starts by going in and doing a reaction and just seeing what you get. And I mean, in many ways, I would have loved to have been a 19th century chemist. There's a lot of ways I'd have hated it. I'm diabetic. I'd probably be dead instead of a chemist. It was a dirtier, smellier era. But nobody knew anything, right? That's a great time to be messing around with stuff. Just go mix some chemicals together, see what kind of tar falls out. Figure out the H goes on the less substituted carbon, and they name a rule after you, and 170 years later, they're still using your name. That's pretty cool. Anyway, so a Russian guy worked about the time that the periodic table came out. There's dispute over who gets credit for the periodic table. Again, cool stuff to think about. If there's a few history of science classes on campus, if you're interested in that kind of thing, you should look into it. So. The fundamental rule that you really need to get here is these addition reactions are always going to give you the more stable cation, right? So if you do a reaction that gives a carbocation, the reaction is going to give you, and a reaction has a choice between where that cation goes, that cation will always go on the position that makes it more stable. That's Markovnikov's rule. So anyway, we take 1-methylcyclohexene, we treat it with HCl. Probably I should have given you some information here. This kind of reaction's often done at extremely low temperatures, right? So the reactions tend to go slower at low temperatures, but they go, right? And so the equilibrium at lower temperatures favors addition. The other thing that's important here, well, I'll do that in the next reaction. Any questions about this reaction right now? All right, this first reaction we're going to do from chapter 8, addition of HX to an alkene. We've got the mechanism. The alkene is going to act as a nucleophile. It's going to attack an electrophile. You'll get an intermediate carbocation, a more stable one, and then the chloride or X, whatever X is, bromide, chloride, bromide, or iodide adds to the positive charge, and you get that product. Okay, I'm going to pause the machine.